Hey, welcome back everybody, and welcome to our online students. Today what we're going to do is we're going to take a look at the three-dimensional shape of molecules. Now up to this point we've been doing Lewis structures, but we've been drawing things like they're two-dimensional objects, kind of like bugs squashed on a windscreen. But in actuality, molecules have three-dimensional shapes, and it's these three-dimensional shapes that give them the biologic activity that we associate with, say, medicines or hormones and steroids and things like that. And an example of this is Nexium. Nexium comes from a company that I used to work for, and what it is it's a molecule that is left-handed. That is to say, it's a left-handed molecule. And you might be scratching your heads going, wait a minute, can molecules be left-handed? Yes, actually they can be left-handed or right-handed, which is a little odd, and we'll explain the chemistry of this and the three-dimensionalness of this. And the reason I like bringing this up is this molecule, this purple pill, we sold about $6.5 billion of this stuff every year. That's not, I mean, you don't sneeze over $6.5 billion. That's a lot of money, okay? So understanding the chemistry leads to some really big innovations in medicine and in healthcare. So we're going to take a look at left-handed and right-handed molecules. We have left-handed and right-handed. We have things like gloves. Gloves can be left-handed and right-handed. We have hands that are left-handed and right-handed, okay? And we're going to have molecules like this. And molecular recognition, this is how we are able to identify certain things, such as things that taste sweet. Sucrose, table sugar, tastes sweet. It has something to do with its three-dimensional shape. There's another molecule that has a three-dimensional shape that also tastes sweet, and that is ethylene glycol, or antifreeze. Antifreeze is a deadly poison, like 50 milliliters of it will kill you, but it tastes sweet. And antifreeze looks like Gatorade, and this is why you keep it away from children. But it has something to do with its three-dimensional shape. So understanding three-dimensional shapes is very, very important in understanding how molecules behave. Now, we're going to take a look at the difference between Lewis structure and shape. Lewis structure and shape, so we're going to go from 2 dimensions to 3 dimensions. And we're going to take a look at bond angles. What are these angles at which these atoms are attached to the central atom? So peripheral atoms attached to central atoms by some sort of bond angle. And there's some pluses and minuses to these different theories. And so we'll touch upon that briefly. Now, this whole theory of this three-dimensional shape of stuff is called VSEPR theory, or valence shell electron pair repulsion theory. That's a big mouthful, so we just call it VSEPR theory. And which I do scratch my head over this. It's called VSEPR theory, but maybe it should be VSEPR theory, but people just say VSEPR theory. It's valence shell electron pair repulsion theory. And the idea is that we have these central atoms with things attached to it. And they could be lone pairs, they could be bonded pairs. And so what we're going to do is we're going to make a table, and it's going to be like our cheat sheet of VSEPR theory. So if you're reaching the bottom of your notebook, you may want to start again up at the top. We're going to make a table, and we're going to fill things in. And this is going to be a chance for those of you that are kind of artistic to be able to exercise those artistic talents. All right, so here's what we're going to do on our table. We are going to make a table, and on our table, I'm going to label it like this. I'm going to go steric number, and then I'm going to go electron pair geometry. Electron pair geometry. And then I'm going to say number of lone pairs. Number of lone pairs, then molecular geometry. Molecular geometry, and then we will do let's do bond angles. All right. Now, for today, I got my favorite Christmas gift from 1993, molecular models. Some people wanted a train set. Some people wanted Barbie. No, I wanted molecular models. And Santa gave me molecular models because I was a very good boy that year. And never again. Now, what we're going to do is we're going to use these models so that way we can see three-dimensional attachments of things. Now, I need to explain a few terms. Now, steric number is the number of things attached to a central atom. And that could be bonded pairs. So let me do this here. I'm going to go like this. Here's my central atom here. Central atom here is in black. So bonded pairs, or it could be lone pairs. And a lone pair might look like this. So these yellow sticks here, these are pairs of electrons. So this would be a lone pair, no atom attached up here. This would be a bonded pair. And we would say then for this, the steric number would be 1, 2, 3. There's 3 things attached. And it doesn't matter if this is a double bond, single bond, triple bond, it just counts as one thing. Okay. Now to get us started, we're just going to start out simple, and then we're going to just add more and more peripheral atoms. So starting out simple, we have 2 things attached. And so we would say then that this has a steric number of 2. Steric number of 2. And then our electron pair geometry. Electron pair geometry, this is our 3-dimensional arrangement of the molecule, including the lone pairs. Now at this point, we don't have any lone pairs. There's no lone pairs with this particular molecule here. And so we're just going to say that this one here has a shape that is linear. Linear. No lone pairs. No lone pairs. And then our molecular geometry. Our molecular geometry is different from our electron pair geometry in that we're just counting the geometry of the atoms. Just the geometry of the atoms. And right now, because we have no lone pairs, they're the same. So our molecular geometry is the same as our electron pair geometry. This is linear. Linear. And then for those of you that remember your geometry, what would this angle be? 180 degrees. Excellent. 180 degrees. Nicely done. Very well done. Now we're going to move on here and get into something a little fancier. We're going to have a steric number here of 3. And here we have 3. 3 things here attached to the central atom. Steric number is 3. Our electron pair geometry, we would say that there's 3 things here and it's all on the same plane. So this becomes trigonal planar. Trigonal planar, so 3 on the same plane. Trigonal planar, no lone pairs, and so our molecular geometry is the same. And for those of you who have spent nights worshiping the Mercedes-Benz corporate logo, what would this bond angle be expected to be? 120. Yep, it's a circle divided into thirds, so this should be 120 degrees. Okay, nicely done. And you remember taking geometry class at some point and you're like, when am I ever going to learn this? Or excuse me, when am I ever going to use this? Now you can go back to your geometry teacher and say, hey, VSEPR theory and chemistry. I'm like totally using this. You're shaking your head. No, didn't take geometry? Didn't like geometry. Yeah, me too. And then I took chemistry and it's like, oh, now it all comes together. Okay, so here now I'm going to take this, still having a steric number of 3, but now I have a lone pair. This is going to be our first one with a lone pair. And so steric number is still 3. Steric number is 3. And our electron pair geometry is still trigonal planar. We're counting that lone pair in our electron pair geometry. We have one lone pair, and then our molecular geometry. Now, molecular geometry, we're just looking at the atoms themselves. And so this, we say, is bent. A bent geometry. A bent geometry. And then our bond angle. What would we expect the bond angle to be? 1/16. Wow. Yeah. Yes. Yes. But it's like, wait a minute. Wasn't it 120 before? What did you do? I don't know, when you weren't looking, right? So what happens? These lone pairs take up a little bit more space in 3 dimensions, and so they will always squish these other bond angles. Now, rather than remembering 1/16, what we're going to do is we're just going to say, well, it ought to be, we might think it is 120, but because it gets squished, we'll go less than 120. Less than 120. 1/16 is very, very particular. All right, so nicely done. So now we're going to move on to steric number 4. Steric number 4. And so we're going to get 4 things attached onto our molecular central atom here like this. Here's 4 things, 4 things, 4 things like this. Okay, so now here's 4 things attached to this central atom. And so we're going to call this one now 4 things. It comes from the Greek tetrahedral. Tetrahedral, no lone pairs yet. This will still be tetrahedral. Tetrahedral. And then our bond angle. Now, up to this point, when we were drawing something like this with 4 things coming off of it, we might draw it like this. Four things coming off of that central atom. And looking at this, we might say, well, that looks like 90 degrees. But it's not. It's not 90 degrees, because now we've stepped into 3-dimensional land. So the bond angle on this is not 90. $109.5. 109.5 degrees. Nicely done. Oh, so then how do you draw this? Well, you could draw it like this, but we want to make it look kind of 3-dimensionally. So we might say, for example, these 2 here are on the same plane as the board. So we go carbon, hydrogen like this. And then we have 2 going away from us. So 2 going away like this. And then we have 1 coming towards us, like this. And so this is trying to show us something that is 3-dimensional. And we can see now that that bond angle is not 90 degrees. So I can guarantee you at some point on a worksheet or a test, you're going to see something like this. And it's going to ask you, what is the bond angle? And if you put 90 degrees, you'd be wrong, because we're in 3-dimensional land now. Okay, all right. All right, now let's move on. Let's see, let's do 4, but let's put in a lone pair here. So I'm going to go like this, like that. There we go. Now this one here, this one is still tetrahedral in that we count all the things attached. There's three bonded pairs, 1 lone pair, so this is tetrahedral. But now our geometry here of our atoms has changed. It's 3 things here, 3 things on the base forming like a pyramid. So if I had a flat place to put this, I might go like that and say it's 3 things like a pyramid, so I'm going to call this one trigonal pyramidal. trigonal pyramidal. And our bond angles on this, we would expect it to be 109.5, but because we have the lone pair and it takes up a little more space, we're going to call this less than 109.5 degrees. We've just squished it down a little bit. Two lone pairs. Steric number is still 4. And our electron pair geometry is still tetrahedral. And now our shape here, we've seen this one before. This is bent. And our bond angle. Now our bond angle is still less than 109.5. And for this one, it gets a little bit particular because this is what water would be. And so this would be 104.5 degrees. 104.5 degrees. This is water. And when we draw this, sometimes we draw water like this, where we have an oxygen, a couple of hydrogens like this, and then we throw a couple of lone pairs like that. But that really doesn't look three-dimensional. And so if we wanted to make it look three-dimensional, we might have a lone pair coming out towards us like this, lone pair, and one going away from us. One going away from us like this, like that, to try to make it look three-dimensional. Okay. How are we doing so far? We're doing okay? All right. I'm just looking here. Okay. It seems stable. All right. This is good. All right. Then we're going to move on to 5, steric number of 5. And well, I think I can get one more here before I have to clean the board. So I'm going to go 5. And I'm going to get 5 things here off of my central atom. 1, 2, 3, 2. Here's 5 things like this, and like this, and like this. Okay. 5 things coming off the central atom. We've got a vertical axis, and then we have a horizontal plane. On our vertical axis, we've got 1, 2, 3 atoms, and then we've got 1, 2, 3, 4 atoms on the horizontal plane. Now this one here, steric number is 5. Our shape for this, it's as though we have a pyramid like this, a pyramid with 3 things on the bottom. It's like a pyramid with 3 things on the bottom. And then we have another pyramid up on this side here. So it's like 2 pyramids with a base of 3. And so we call this one trigonal bipyramidal. Trigonal bipyramidal. So it's like a base of 3 with a pyramid, and there's 2 of them. No lone pairs yet. And so our molecular geometry is the same. Trigonal bipyramidal. And then our bond angles. We're going to have a few of them here. This one here would be 90 degrees. And then this one here is going to be 120. $120. And if I were to draw this, what I might do is have 1, 2, 3 on the same plane, and then have one coming out and one going away. So I might go like this, and here's my vertical axis, okay, like this. All of these are on the same plane. All of these are on the same plane. Now these 2 here, I've got one going away from us, so we'll go away from us like this. And then I've got one going towards you out of the board. So like this, like that. Artistic representation. Trigonal bipyramidal. Okay. Nitrogen triiodide. And if we were to add up the valence electrons for nitrogen triiodide, nitrogen has 5, iodine has 7, and there's 3 of them, which brings us to, that's 21 plus 5 is 26. 26 valence electrons. Nitrogen's going to go in the middle. And we're going to make single bonds to these iodines, like this. And then the next rule is we need to fill in those lone pairs. So those lone pairs, oh, wait a minute, that's not iodine, that's hydrogen. What am I doing here? Okay, fill in the lone pairs on these iodines. Well, I's kind of look like H's when you're laying on your side. That's my excuse. Okay, there we are. There's our lone pairs. And then I add up all of these electrons in my molecule compared to what I should have. So I've got 2, 4, 6, 8 times 3 is 24, which means I'm too short. So those 2 electrons go where? On the nitrogen. So we're going to put a lone pair right here like this. Now, what is the steric number on nitrogen triiodide? 4. We have 1 lone pair. So our electron domain geometry would be tetrahedral. And then our molecular geometry would be trigonal pyramidal. Excellent. Okay. Where was I? Ah, yes. Okay. Steric number of 5. We have 1 lone pair. Now, it does make a difference. It does make a difference where our lone pair is. If our lone pair is here, our angle is 90 degrees. And if it's here, our angle is like 120-ish. And in nature, what nature does is it likes to put that lone pair on this equatorial plane, so that way there's a larger bond angle. And this is because that lone pair takes up more space. And so it's going to be on that equatorial plane there, this equatorial plane. All right, so now our geometries and names for this stuff. Our electron pair geometry is still trigonal bipyramidal. 1 lone pair. And then our molecular geometry, oh, this brings me to one of my favorite stories. When I was a kid, on playgrounds were a little different than they are today. Back in my day, we didn't have like wood chips and pea gravel. We had asphalt and broken glass. And monkey bars were just like by some plumber who was dating Dr. Seuss, because they were all just kind of strange like this. Now, we had these things on the playground called teeter-totters. And a teeter-totter, what that was, it was this sort of a thing like this that would go like this, right? And so you would sit here and you'd have your friends sit there, and then you would like jump off, and then they'd come crashing to earth and end up with spinal compression and nerve damage. And we called this fun. So this shape is, there's another name for teeter-totter. This is called seesaw. This is a seesaw shape. And our bond angles on this, we'd expect our bond angles to be 90 degrees and 120 degrees, but because we have that lone pair on there, well, we'll say less than 90 and less than 120 because of the lone pair. Whenever you have a lone pair, expect to see something most likely being squished. And then if we have 2 lone pairs, and we go like this, That's also going to be on the equatorial plane. So we're going to have 5, steric number of 5. We're going to have 2 lone pairs. Our electron pair geometry stays the same, but now our molecular geometry is different. We're just looking at the atoms here. And this is going to date me a little bit here, but I pity the fool who doesn't know VSEPR theory. I pity the fool. This is T-shaped, like Mr. T, like the A-Team from a TV show before you were born. Never mind. Okay, so this is called T-shaped. He made a movie with Bradley Cooper. Okay, this is T-shaped. All right. And then our bond angles on this, we'd expect this to be 90, but because we have the lone pairs, we might say less than 90 degrees. And if we had one more lone pairs, let's see here, we're going to have 3 lone pairs, 5, still trigonal bipyramidal. Our shape is now, you've seen this one before, linear. And our bond angle, there are lone pairs on this, but we would still expect this to be 180 degrees. 180 degrees. Then that's going to take us through steric number 5, and our last steric number is going to be 6. This will be our last steric number, is 6. Steric number of 6. No lone pairs. Our electron pair geometry, if we were to imagine that this was like these peripheral atoms were connected, you'd have a pyramid here with 1, 2, 3, 4 sides on the top, and then 4 sides on the bottom. And 4 and 4 makes 8. And so this one we would call octahedral. If you played Dungeons and Dragons, this would be an 8-sided die. Octahedral. No lone pairs. Our molecular geometry is still octahedral. And our bond angles, we'd expect these to be 90 degrees. 90 degrees. And we're going to do a lone pair. So lone pair, steric number is 6, still octahedral. Now our shape here is going to be square on the bottom, 4 things on the bottom, and a pyramid. We're going to call this square pyramidal. Square pyramidal. And our bond angles, we'd expect these to be 90, but we've got a lone pair on there, so we go less than 90 degrees. They're going to get squished a little bit. And then 2 lone pairs. 2 lone pairs, they're going to be opposite of each other, trying to take up some space here. So 2 lone pairs, steric number is 6, octahedral. This now is going to be square planar. Square planar. And our bond angles here, we've got lone pairs pushing, but equally and oppositely on opposite sides here. So we'd expect this to be 90 degrees. 90 degrees. Okay. Now, any questions on any of that? In your textbook, there are some diagrams which gives you the steric number, gives you some bond angles on there, so on and so forth. What we want to do then is take a look and see if maybe we can't make a little bit of a prediction here. So for example, here's a molecule, formaldehyde. Formaldehyde is that stuff that they used to stick or preserve animals in biology class back in the day. And so this has a formula of CH2O. And the question is, what's the molecular geometry going to be on formaldehyde? So CHO2. Okay. CH2O. Right? Is that what I have there? CH2O. Okay, so I need to do my Lewis structure for this. And I can count up my valence electrons. Carbon has 4. Hydrogen has 1 times 2 hydrogens. And oxygen has 6. So that's going to be 10 plus 2 is 12 valence electrons. And then I need to pick my central atom. Now, this is a little trickier. Up to this point, we've just picked a central atom, whichever element there's only one of, which means it could be carbon, it could be oxygen. Probably not going to be hydrogen. But then the question is, which is going to be our central atom? Which one's furthest to the left on the periodic table? Carbon, generally. Okay. So carbon's going to be our central atom. And I'm going to make some single bonds here like this. Going to go oxygen, hydrogen, hydrogen like this. Then I complete the octet on my peripheral atoms. Hydrogens are already full. Don't want to add more. Oxygen, go like this. Okay. And then I add these all up. 2, 4, 6, 8, 10, 12. That matches. But carbon does not have an octet. And so I need to give carbon octet. I'm just going to take one lone pair here, make myself a double bond. So now that I've done that, my steric number, what is my steric number for this molecule? It's 3. We count this as one thing, even though it's a double bond. So my steric number is 3. And so if I were to draw this a little bit better, maybe, what I do is I try to make these bond angles equal. So I'm going to put a carbon, double bond oxygen, like this, like that, like that. See, right now this looks like a T shape, but it's actually going to be more like a Mercedes-Benz symbol. All right, so my electron pair geometry, trigonal planar. My molecular geometry, trigonal planar. And then my bond angles. We'd expect it to be about 120 degrees. We'd expect it to be about 120 degrees.